here I am with my car entry. So let us say I have two cars, but these are very special ones in a way that they have identical linear model and they are autonomous. So passengers sitting inside a car don't have to do any work. And they are provided with a controller. So controller can takes care of everything or its operation, and in addition it is provided with the ability to initiate communication with controller in another car, so they can exchange information. Now assume that there are two friends who are headed for a long drive, and they want to maintain distance between their cars below D max. So guy 1 is sitting in car 1, guy 2 is sitting in car 2, and this is what they ordered to controller. Now it is controller's job to do this work, and this is what we mean by synchronization. We want to maintain the difference between car below D max over the entire journey of their travel. So when controller initiate or activate the communication channel with controller 2, they can start exchanging information, and using information about other car and using that as a feedback, they can make sure that distance remains below D max and everything works. But the problem is this channel is very expensive. The longer you keep it on, the more cost you have to pay. So it is not economical. So controller has to do something to tackle this problem. Controller can switch off the communication, but the problem is as soon as you switch off the communication, they don't know information about other cars. Now you may say that cars have identical dynamics and car 1 can predict information about position of car 2. But the problem is this can happen in computer simulation, but in the real world there is always disturbance, and which will make sure that it is not possible to predict the position of other cars. And as soon as the communication is turned off, the two cars are following their individual dynamics, and with the disturbance they will try to move away from each other, and the distance will exceed below D. So we say there is a clear trade-off. When communication is on, the distance is below D max, but cost is high, and when we keep the communication off, cost is 0 but distance exceeds. So there is a trade-off, and we have to do something to tackle this problem. So our idea is to keep communication on and off intermittent. So we will allow cars to communicate for some duration. With the communication they will come together for some time, and at that instant we will switch off the communication. So disturbance will come into picture, and again the cars will try to go away from each other, and at some instant again we will switch on the communication. So we will intermittently switch on and off the communication in such a way that both these objectives are met. The distance remains below D max throughout the whole journey, and link is on for minimum possible duration. So that is our problem, to come up with the optimal strategy of switching between communication and no communication case. So you see this example of cars is just illustrating. The problem behind is very general. Think about telecommunication system. We know that for proper communication, the frequency of transmitter and receiver should be equal. So here we can replace cars with transmitter and receiver, and the distance is equivalent to frequency difference between them. So we want to minimize this difference. We want to maintain this difference below the bounded value. Similar case with the power system. When we want to connect some power source, energy source to the power grid, we want to make sure that phase difference of source and power grid are exactly equal, or should be remain some bounded value. So here again we can replace cars by sources, and the distance is equivalent to the phase difference between the two cars, and that is what we want to minimize. Now we have just considered the two systems here, but the problem becomes even interesting when we have multiple systems and we want to minimize their distance. Thank you.